Welcome back. So in this section, we'll be covering deploying BGP, mostly best practices. So we will discuss about the role of IGPs and iBGP, aggregation routes, why we need to aggregate, receiving prefixes, origin Ace validation, preparing the network and configuration tips. So IGP, for the question that was asked earlier, it is internal routing protocol or interior gateway protocol. The two examples are ISIS and OSPF. Some prefer ISIS, some prefer OSPF. Either one will do a pretty good job. It's used to carry infrastructure prefixes. So infrastructure is internal interface IP addresses, loopback IP addresses. It's not recommended to carry anything other than the infrastructure IP addresses. So the design goal is to minimize the number of prefixes in IGP to speed up convergency within IGP. Remember that BGP recurses to IGP, so it's very important to have a faster IGP convergency. BGP is used both internally and externally. Internally, it's used to carry non-infrastructure prefixes, and externally, it's used to exchange prefixes with other service providers. And there are different scenarios for that. We'll discuss that. It can scale to a large number. So that's why we don't want IGP to be burdened with customer prefixes. It impacts its convergency. IGP is designed to converge faster, which means very, very fast in sub-seconds usually. So we don't want to burden that to increase the convergency. So the main objective is to minimize the amount of information carried in IGP, just enough for BGP next hub. And of course, you should be able to reach the infrastructure interfaces for management purpose as well. And with eBGP, that's where you apply policies. What routes to update, what routes not to receive, and when you receive, how you prefer those routes. Again, the same representation we saw earlier. IGP is within an internal, within a single domain, and it doesn't breach domains. It doesn't breach autonomous systems. So the IGP in AS1 doesn't exchange routes with IGP in AS2. iBGP is used to carry, exchange routes within a single AS, but that same route could be exchanged to another AS via eBGP, subject to policy, obviously. So that's a clear difference. So the do nots, very important here. Do not distribute BGP prefixes to IGP. Otherwise, you will run into 500,000 routes into your IGP, which doesn't scale. In most cases, you will get probably a router crash or a huge scalability delay. And do not distribute IGP routes into BGP. There are ways to inject routes. One way is to redistribute IGP into BGP, but it's not advisable. It's better to use network statements to inject routes into BGP instead of redistributing IGP into BGP. So do not use IGP to carry customer prefixes. Use your iBGP to carry your customer prefixes. It doesn't scale and you don't need to do that. So injecting prefixes into iBGP. How do we inject prefixes into iBGP? It's usually used to carry customer prefixes as well as prefixes connecting for interfaces connecting to customer, as well as dial-up interfaces and so on. Some of the techniques that you can use to inject prefixes, customer prefixes into iBGP is you can point a static route to your customer and then enter a corresponding network statement into BGP. Okay? Another way is you can even create, if you are receiving, you can even create, in some cases, you can use techniques where you create also another static route pointing to a null, but with a very high distance, so that even if the interface to the customer goes down, if the interface to your customer goes down, your static route will also go down. So that will create a BGP ripple effect. So to avoid that, you can use a static to null with a higher distance so that the BGP routes, the customer prefix still remains in BGP table even if the connection to the customer goes down. So that improves stability to your network. So when do we use, so in some cases you may use eBGP with customer. Normally, if that customer is using your prefix, and if it is single homed, you don't really need to use eBGP, to run eBGP with customer. The BGP is used if your customer has autonomous system assigned from a registry. It has its own IP address assigned from a registry. Then you need to carry that customer prefix because it doesn't belong to your, and the other requirement is if it is multi-homed, if it is connected to other service providers as well. So if the prefix is assigned from your own address space to the customer, then the customer cannot advertise through another service provider because it's your prefix. So in that case, you don't need to use eBGP. You can just use a static route pointing to the customer. Aggregation, quantity versus quality. So when you have prefixes, you can aggregate them. Normally, when the prefixes are assigned from a registrar, you split them and assign them to different customers and to different parts of your network. And internally within your network, there will be sub-prefixes. But when they are advertised to external peers, they should be advertised as aggregates instead of sub-prefixes. That improves stability. That improves convergency, both for your customer as well as for the internet. Unfortunately, too many people advertise sub-prefixes. Too many people advertise /24s, even though it's not expected to see, based on the registrar, the registry entries, most should be, you should only see very few /24s because most assignments are /22 or shorter. So the basic rule of thumb is when you advertise to peers, advertise only your aggregated route or the address space assigned to you instead of the sub-prefixes, and block the sub-prefixes from being advertised. If you have to advertise sub-prefixes for traffic engineering purpose, there are other techniques instead of advertising the same sub-prefixes that are assigned to the customer, and we'll discuss that. So ISPs, so why do ISPs don't aggregate? One of the main reasons that they give is traffic engineering. But it's very important that because if you don't aggregate, then you increase to the number of internet routing table. And the increase in the number of internet routing table reduces the convergence time, it increases the instability of the internet. So it's highly advisable to aggregate. So because of that, if you don't aggregate, your service, your ISP is considered poor by the ISP community. So it's important to aggregate. So here is a bad example, and we'll see a good example, and why it is important to aggregate. And if you don't aggregate, it's not just you are hurting the rest of the internet, but you are also hurting your customer. So here, customer has /23 assigned from your block. So assigned from the AS100 address space, and when the AS100 advertises routes, it advertises both the super block, which is /22, as well as the sub prefix, which is the /23. Okay. Now, let's see the impact. Customer link goes down. What happens? When the customer link goes down, the route is withdrawn from iBGP. When the route is withdrawn from iBGP, since it's advertised via eBGP, it's also withdrawn from eBGP. When the route is withdrawn from eBGP from your next peer, it also has to withdraw it from all the advertisements that advertise to other peers. And the whole thing propagates, ripples through the internet. And when the interface comes back, when the interface comes back, the same thing happens again. The interface is injected into iBGP and then advertises to the eBGP peers, and the whole thing propagates all over again. And if you are only advertising the specific prefix, the customer may not even be visible to the internet for a long time, as some service providers dampen advertisements and use hold down to reduce instability. So this doesn't give quality for your service, for your customer. It doesn't also give you quality for the rest of the internet. So it's very important to aggregate. Here's a good example. You allocate /23 to your customer, but you are advertising only /19 to the rest of the internet, which is a superset of that /23 and number of other sub-interfaces, the sub-prefixes. Now, when the interface goes down, it is withdrawn from iBGP, but nothing happens to the rest of the internet because it's not being advertised to the internet, so it will not be withdrawn. Traffic to that customer will come to the ISP, and it will be dropped at the border router because there is no route for it. But as soon as the interface comes back, then it's injected into iBGP, and traffic immediately flows to the customer. Good for the customer, good for the internet, and creates a stable internet. So it's very important to aggregate. So you can see that aggregation increases stability of the internet, reduces the size of the routing table, which also contributes to the stability of the internet. It reduces route churn, and it improves quality for everybody, not just for your customer, not just for the entire internet, but for everybody. But many service providers do the bad example. And there are part reasons, but some of the reasons are not acceptable. So in some cases, it is lack of knowledge. It could be lack of knowledge. It could be just laziness not to go through the a rigorous process of reducing the size of the table. So, and we'll come back to that. We'll see some examples and some efforts to improve that stability. So separation of iBGP and eBGP. So it's very important that what you carry within your iBGP and what you carry on your eBGP, you have to look at it at two separate entities and apply two different policies. iBGP is where all customer prefixes reside, where all your non-infrastructure prefixes reside, including customer-facing interfaces. eBGP is where your aggregate prefixes are advertised. In your iBGP, you have your sub-prefixes exist as they are without being aggregated. You will still have the aggregate, but since you have the more specific route, the more specific sub-prefix will be used within your iBGP. But when you advertise, it's very important that you advertise aggregate prefixes. If you need to do traffic engineering, do not use the customer prefix. Generate a different set of prefixes which are a superset of the customer prefix, but a subset of the allocated prefix. And by doing that, since you are generating them with probably a static route nailed down to null zero, by doing that, you improve the convergence because those prefixes are always advertised irrespective of the state of the customer interface prefixes. Okay. So, internet table today. So this is, even though it says today, I captured it in July. So in July, we have 420,000 routes. You know, by now, probably it may creep up to 430. So this is the total number of routes on the internet. But when you do analysis, if you do a CIDR-based aggregate, you can reduce it by half, close to half, as you can see, to 243,000. And if you do the maximum aggregation, even doing a superset of the CIDRs, you can even get down to 181,000 routes. So you can see that if people do their homework of doing the aggregation properly, we can reduce the size of the internet table by 50%, essentially. Again, there may be some reasons in some cases that may not be the case, but there is a long way, there are lots of things that can be done to improve the stability. So the new swamp. So in the past, it used to be, this is probably 10 years or so ago, it used to be the 192/8 address space was the swamp space. The swamp space is where you see a lot of /24 addresses, prefixes on the internet. So as you can see here, this is from 1999. In 1999, you can see that the 192/8 has over 6,000 /24 prefixes, or sub-prefixes, total sub-prefixes. So the 192/8. But most of the other blocks did not have large number of sub-prefixes. But today, actually 2 years ago, you can see that a number of blocks have a lot of sub-prefixes. So you have so many new swamps. So you can see there 64.8 has 6,800, 66.8 has 7,700, and so on. So there are lots number of new swamps creeping up. Okay. So it is important that if we continue with this, if we have all the 120/8s with an average of 5,000 prefixes per block, it will get to 635,000 routes. If we have 6,000 routes per block, then per /8 density, then we'll have 762,000 routes. So you can see how it could easily increase. So all this is to stress the importance of aggregation. Okay. So what are the real reasons for aggregation? So deaggregation, not aggregating. In some cases, it's lack of knowledge. In some cases, it is just laziness, not doing the homework. In some cases, deliberate knowing actions knowing the impact. There may be some valid traffic engineering cases, but most traffic engineering cases can be solved without doing extreme deaggregation. So there have been efforts to improve the aggregation or the deaggregation issue, and one of them is the CIDR report. It was first started by Tony Bates and later on revised by Philip Smith, who developed this tutorial actually. I updated it, but he developed this tutorial. So he continued with that effort, and now it's combined with Geoff Hoston's routing analysis. And you can go to the CIDRreports.org website, and you will see a lot of reports, weekly reports, showing the trend. And we'll see some of those reports. It computes the size of the routing tables. It provides suggestions. It sends emails to the service providers, reports, as well as suggestions on improving aggregation. Here is from the website, here is a summary. Here you will see, this is in July, you will see the CIDR aggregated and actual prefixes. So in that case, it is 419,000, and if they are aggregated, they could come to 241,000, and so on. And you will see that list. Here is a more specific one. In this case, it's actually showing, this is showing the top deaggregated prefix service providers. So in this particular case, this week, Bales House was the winner, essentially. So if it was aggregated properly, it could save 94.4% saving. So it was a lot of deaggregation. So they generate these types of reports and send out the reports. Here is another one that shows the top 20 route counts per originating S, how many routes they are originating. They may have multiple blocks, so it doesn't mean they are the worst deaggregation. It's just how many routes they are injecting into the internet. Top 20. And this is a weekly, and it also captures the change between weeks. Here it shows total prefixes again per S. And here it is a suggestion. Now, for a specific autonomous system, what can be withdrawn and replaced to improve aggregation. So, so the importance of aggregation is it reduces the size of routing table for the entire internet. Normally, your own, if you are taking the full internet routing table and you add your own infrastructure and customer prefixes, the total number of routes in your BGP table or iBGP table is actually much larger than, much higher than the internet routing table. In some cases, some of the big service providers, even by 120,000 more. So some may be even more. So total number of routes could be even higher than what you see here for a specific service provider. So it improves convergence when we do aggregation. It reduces CPU cycles, or normally when you have a router and doing convergence, you want the router to go full speed and consume all the CPU to convert faster. But if you have a large number of routes, it will stay full CPU for a long time, and it could have adverse impacts depending on the operating system. Here's another website that provides updates, the Potaro website, and the BGP update websites, and shows BGP instability. So this shows you how many prefixes up downs per prefix for a specific customer, and shows also again for the top customers. The top customer in this case was the one that you see there. They had 17.8 updates up and down per prefix for that particular service provider. Here it is total number of up and downs per service provider. Here this graph shows the size of the internet table growing. The top line shows the size of the internet table growing. The x-axis is year, 2012, 2011, and so on. The second line shows aggregation based on AS paths. The third one shows aggregation based on AS origin. So keeping the same AS paths, if we aggregate it, we'll still go half, almost half. If we aggregate it based on the AS origin, we may even be better. So there's a lot of room for aggregation. That's basically what this graph shows. So the next message is aggregation on the internet could be much better than what it is today, but it could be it can be reduced by up to 35%. There are tools and available commands to analyze and implement these changes, but still you see a number of people doing a lot of deaggregation. Okay. Receiving prefixes. So receiving prefixes in this case means via BGP. Okay. So you can receive prefixes via BGP either from a customer talking eBGP with your customer, or a peer, or a transit provider. A transit provider is where you send all your traffic if you don't have any other exit points. So it's your default traffic if you don't have multiple transit providers. If you have multiple transit providers, then you pick the best path. You receive full updates from both, and then you pick the best path. So from customers, you should only accept updates from BGP updates from customers under the two conditions shown below. If the ISP has not assigned address space to the customer, so if the customer has its own address space received from somebody else, from the registries essentially, and when that happens, you have to check with the registries whether that address space is really assigned to that customer, and you can use a who is information to do that. So that's pretty simple. And then, if it is a valid assigned address for that customer, then you can receive it and send it upstream to other service providers. Okay. And this is an example of a who is information. In this case, it shows assigned portable. So it means it is assigned to the customer and can be received and advertised by a service provider. In this case, it shows allocated, unspecified, which means this is actually allocated to a Verizon. So if a customer comes to you and this is my IP address, you cannot, it may have been assigned to that customer by Verizon, but it doesn't belong to that customer, so the customer cannot advertise to another service provider. So you should not receive that prefix from that customer. It should be a prefix assigned to the customer. Receiving prefixes from peer, usually this is based on an agreement. The two parties agree what prefixes to receive and send, and then they will implement their filters to receive and send and block prefixes from the different service providers. Okay. And you can also use the Internet Route Registry to verify the origin of the AS, whether that route is registered. And you have to have, you also have to have, once you agree, you have to document it either via email documentation or some kind of documentation. Another way to validate a specific prefix belongs to an autonomous system is using Origin Ace Validation, RPKI infrastructure, and we'll see that. So this is an automated means to check whether a route received from a peer really belongs to the AS it is originated from. And we'll see that how it works. Any questions? Receiving routes from upstream transit provider. If you have just one upstream transit provider, there is no need to receive full internet routing table from that service provider. You just receive a default route from that service provider. If you have multiple upstream service providers, obviously you will need to receive the full internet routing table. But when you do that, you have to make sure that prefixes you received from peers and from customers are preferred over prefixes received from your transit provider. Okay, and you can use policies to do that. Okay. It's important when you receive prefixes from peers, even from customers, to make sure that, actually from transit providers, when you are receiving a full internet routing table, it's important to make sure that when you send, you remove any private AS. So you have to put a filter to remove private ASs. You have to make sure that you are not advertising any private address space, and it's shown there from the list. And it's important to make sure that you don't receive or advertise any prefixes, bogon prefixes or bogon ASs. So you have to implement those prefixes, those filters. Okay, so for bogons, you can check the Team Kumri. I didn't know that it's pronounced that way, but I came to know about it recently. So it's pronounced as Team Kumri. So Team Kumri publishes bogons. You can also get bogon list from their server. So you can get, there's an automatic way of getting a bogon list, and you can go and check their website there. They also have configuration templates for different vendors on how to filter bogons. So it's a useful tool there. So making sure that you are receiving the right prefix, making sure that you are not receiving bogon prefixes or private IP addresses or bogon advertising private AS numbers and so on is very important for the integrity and stability of your own network as well as for the entire internet. So it's very important to pay attention. So we discussed that you can verify the validity of a prefix using BGP Origin Ace Validation. This is a new draft, actually. It's not even yet a standard. There are parts of it a standard, but not a full standard yet. So it uses our RPKI infrastructure that we'll discuss later on. But first, let's discuss the problem. Problem is, right now, any AS can inject a prefix unless you filter it, obviously. So I can inject a prefix into the internet, and that could create what's known as prefix hijacking. So it could create a problem where I may say, I may advertise Google's prefixes and everybody's sending Google traffic to me, so Google not receiving any traffic at all. Right. So to avoid that, it's important to validate that the prefixes are advertised from a valid origin AS and by a valid entity. And you can see actual incidents there, the number of incidents, and the one particular one, although I'm not sure, let me see. Okay, let's go here and then we'll see the example. In this particular case, let's see the valid prefix owner is AS40, and AS40 advertises that prefix upstream to a client, and also AS20 advertises that same prefix with the same prefix length upstream. Now when AS10 gets it, AS10 compares the two prefixes. The shorter AS path length wins, so it sends the traffic to AS20 and gets black-holed. So that creates a problem for this. Maybe if that's a web service provider, they are not getting the traffic. So it creates a problem. So this is one reason. So with the prefix length is not different. It's just the AS path length creates a problem. Second problem is, even if the prefix length, the AS path length is the same, somebody may advertise with a shorter prefix length. So they may advertise my 10.24 as 10.24 as 10.25, and maybe at 10.127/25, 120/25. So now my prefixes, so that the prefix advertised with smaller, with more specific prefix is preferred over less specific prefix, right? Because of that, all the traffic for that prefix goes to the wrong recipient, and these both cases are called prefix hijacking. This happened, I'm not sure if any of you remember, happened maybe a couple of years ago to YouTube. I think the Pakistani government wanted to block YouTube and told some of the service providers there to block it. And to block it, and instead of blocking the traffic, what they did was they injected a more specific prefix. I think it's the Pakistani Telecom, injected a more specific prefix of YouTube, and all the traffic for YouTube went straight to Pakistan. And YouTube was down for, I'm not sure for how long, but at least for hours, if not for a day. So that it's something that happens in real life. So it could happen. So how do you avoid these types of problems? And one way is to use the origin validation. So the origin Ace validation. So here it shows you some of the standards, the IETF drafts and the RFCs. But if you go to the Secure Internet Domain Routing Working Group website, you will see all the drafts, as well as the internet drafts, as well as RFCs. So RPKI, the Resource Public Key Infrastructure, is a globally distributed database. It gets its information from the registrars, and it basically verifies the authenticity of a prefix and its origin AS, what the origin AS should be. So here is how it looks like. So in this particular case, you can see that the top one that you see there is RPKI infrastructure, and the bottom one is a router. So the router talks with the RPKI cache and receives ROS, or route origin authorizations, for different prefixes. So now the router has in its database a prefix and an authorized origin AS in its table. Now, when the router receives in an eBGP update, when a router receives a prefix, it checks that prefix against the ROA. Depending on what if it is found inside the database, either it is valid or invalid. If it is not found in the ROA database, then it's classified as unknown. Okay. So now 3 states: unknown, valid, and invalid. Based on these 3 states, then you can make routing decisions. So here's an example. Let's say the router has an ROA of 10.0.1/24 as being it has an array of shown on the right side and receives a route which is 10.01/24, and it gets a match which matches the AS that's received. So now that's a valid route. In the second case, it gets a match, but the AS number doesn't match with the ROA. In this case, it is invalid. This is the most suspicious scenario, when it is invalid. The third case is it didn't get any match. So it means that prefix is not registered into the RPKI infrastructure. So this router has not received ROA entry for that prefix. In that case, it is unknown. Once the router receives that information, it communicates that information to all the iBGP speaking routers in the network via extended community. Remember, we discussed about community. Another attribute is extended community, which is much longer version of a community. So in this case, the extended community is used to communicate the validity of a prefix. So other routers do not need to reclassify that traffic, and they don't have to do ROA check. So based on that, you can implement a policy. You can say, if it is invalid route, do not send traffic to that route, or use make it less preferred. Use a local preference of, let's say, very, very low. If it is valid, very high. If it is unknown, medium. You can also decide, if it is invalid, I'm not going to advertise it. But if it is valid or unknown, I will advertise it. So you can implement different policies. But this is just the infrastructure for checking that. Okay. Any questions? Yeah.
Hi, my name's Arthur Plato. I'm with the Coldwater Board of Public Utilities. How do you check to see if your entity is in the ROA, and if it's not, get it published into the ROA?
I can point you to links, but you should be able to find that from the registry, and you can peer with ROA, with the RPKI infrastructure, using your router, and get that information as well.
Okay.
If your router supports it.
Okay.
It's a new implementation, so some of them may not support it.
Okay. If you're running an iOS XR, it runs RPKI?
Depending on the release. So the latest releases do support it, yeah.
Okay. Thanks.
Welcome.
Sandy Murphy, Sparta. To expand a little bit on that answer, you have the ability right now in any of the RIRs to generate certificates and ROAs for your prefixes with some care in wording about whether or not you have to be a member of the RIR or not. And once that information is generated, then the RPKI gathering tools will discover it. Right. So the part of his question that said, and if it's not there, how do you get it there, is you work with the RIR systems. They have hosted systems, web pages, click on buttons, and ROAs are created for you.
Thanks for that information. Any questions on Origin Ace verification? So the other key thing is, when you do that, since we use extended community to communicate that information, even though you can use that information and just set the route attributes to influence routing decision, you can also have the option of communicating it with extended communities. But if a router doesn't support the Origin Ace validation, they may not even support the extended communities. But you can still use at the border routers that support us the Origin Ace validation, and then set the right set of community values, regular community values, or right set of local preference, and influence the routing decision. Okay, now how to deploy BGP. So in this particular case, what we'll do is we'll just start from scratch. We'll assume that you have a network with just static routing, and then go from there. Since we are running BGP, obviously, you'll need autonomous system number. If you are playing around, you can use a private AS number. If you are doing it on a real network, then you better get it from the registries or from authorized service providers. So again, the initial assumptions is you don't have IGP, you don't have BGP, you only have static routing. So your network is pretty much simple and dumb. Now, I think you're blocking it. Sorry. So the first step is the transmitter was being blocked over there, so I couldn't navigate it. So the first step is to decide what IGP to use. Again, OSPF or ISIS, depending on who you talk to, some people really prefer OSPF, some people really prefer ISIS. There are some differences, and I would say whichever you feel comfortable. And if you have a staff if your staff is more conversant with OSPF, you can start with that. Some advantages like OSPF, if you want to run V6 and V4, then you need to have two different processes. V6 is OSPF V3, V4 is OSPF, so there is that difference. With ISIS, you can run ISIS and run V4 and V6 at the same time using the same process, so you have that advantage. But other than that, they all have similar features. Most vendors implement the same features on both routing protocols. One may get one before the other, depending on how the standard process goes. Usually, ISIS gets some of the features quickly before OSPF, but eventually all routing protocols get those features. It's important to have a loopback interface on all your routers, and the loopback interface will be used for BGP peering, as well as BGP router ID, as well as OSPF router ID if you are running OSPF. And you can deploy IGP OSPF without impacting your current network. Remember, you are running static routing, and in most cases, static routing has higher preference over dynamic routing. Usually, static routing has a distance of 1, whereas OSPF has a distance of 110. So if you implement OSPF, current routing will not be impacted because the static routing has preference over the dynamic routing. So you can implement it without any impact to your current network. And eventually, you can start getting rid of your static routes one by one. So it's important when you do IGP, your infrastructure interfaces, that interface connecting your routers, router interconnection, not interface connecting to the customer. You don't put that into IGP. Only interface interconnecting your internal network, you put into IGP. Interfaces, the loopback interface has to go into IGP because if it is not in IGP, then you will not have your eBGP session, your iBGP session will not be established. So that's another important thing. So routes which don't go into IGP, your customer routes, obviously your BGP routes will not be distributed into IGP. DSL cable interfaces, those dynamic IP addresses, you don't put them into IGP. You will put them into BGP. So it's basically just the network interfaces. Your DMZ should not go into IGP. That's also another important thing. It's basically your interfaces, infrastructure interfaces, and loopback IP addresses. The second step is to establish the iBGP session, the iBGP peering, before you even establish eBGP with other service providers. And You can run iBGP on all your routers. You can run iBGP on a subset of the routers. It's possible that your router may not support, some of your routers may not support BGP, but the core of your network has to have BGP. So we'll see each scenario later on. So if you are going to peer with two different service providers and you are going to be a transit, then all routers in the transit path should be running BGP. So in this particular case, for example, A, D, and B should run iBGP because they are transit. The reason for D is a transit because A-B link goes down, traffic will go through D, so it's still a transit. So if you look at traditional, I would say, layering, in some, you can take it as a general rule, a guideline. Not everybody sticks to this, but if you take this guideline, if you have a core distribution layer and aggregation layer, now you can, in the core, you'll obviously be running BGP. Okay, it's usually a transit path, so you will have to run BGP. In the aggregation and distribution, it is optional. Obviously, if you run BGP in the aggregation, you have to run in the distribution. If you run the aggregation, you have to run the distribution. So one of the problems is many aggregation devices do not support BGP, in which case you don't run BGP on those devices. You can just run static routing or IGP, but not BGP. Distribution, usually you'll run BGP in the distribution layer, but it does not have to run BGP. If it is not a transit, you don't need to run BGP. But if you are going to grow, it's very important that your distribution layer also runs BGP. And if you intend to grow, it's better to do it from day one. In the core layer, obviously, BGP is important because you're going to be a transit point. That core is a transit point from one service provider to another. So it's important to run BGP. You must run BGP there. It's also where you have your border routers, the edge border routers. So you will need to run, obviously, BGP there. You have to decide on iBGP policy. So on your iBGP peer, you can classify iBGP peers into subsets. Some routers receive full table. Some routers receive only infrastructure and internal and customer prefixes, but not full table. In that case, you have to distribute default routes either via IGP or via BGP. And then prepare the network to deploy iBGP. Okay, let's go quickly. Installing customer prefixes into BGP. So it could be that it is a customer assigned prefix. If it is a customer assigned prefix from your address block, then you can use static route and network statement to inject it into your network. If it is a rare registry assigned IP address or prefix, then you can receive it via BGP. Then after you implement, then you can carefully remove the static routes and make sure that everything is working. Remove one by one and make sure that everything is working. So the key here is the steps shown are not flag day. You can do them one by one. Step by step, do one week, another week during maintenance window, and so on. So the configuration summary, you need to have IGP, you have to pick your IGP, implement IGP. Customer prefix should go into iBGP, not into IGP. And then for your edge devices, like for your distribution routers or aggregation routers, you can decide whether on sending full routing table or partial table as well. Okay, so here is another reminder. Make sure loopback is not configured on router. It should be configured on a router because you'll need it for your IGP if you are running OSPF, and you'll need it for BGP peering. You'll also need it for BGP Next Hub, which we'll discuss later on. On DMZ, you can use, there are multiple ways. One way is to not use the default Next Hub, and instead use Next Hub self, which we'll discuss later on, which is this is the Next Hub self. So the Next Hub self is, by default, when you advertise a route received from eBGP peer to your iBGP, the Next Hub is set to the eBGP peering address and is not changed. The recommended way is when you send updates, route updates received from your eBGP to your iBGP peer, set the Next Hub to the loopback IP address of this router. It's important to, if your router supports it, limits the AS paths received. That means you can block the updates received from your peers based on AS path lengths. This is showing how some of the updates are really, really long. The second one is because of, first one is because of implementation errors. Second one is because of large number of prepends, which is unnecessary. Another important mechanism, use GTSM, TTL security mechanism. If your router supports it, supporting this makes your eBGP peering much secured because it will not be accessible to anybody outside the two routers. Because in order for the traffic to hit the router, it has to have a TTL of 255 or 254. If you are one hop away, it will be 253. So the router will automatically drop it, in most cases, in hardware without any impact to the router. So it is a good security mechanism. Templates are very important. Most vendors support templates for neighbor groups, for session groups, for policies. So it's important to use templates. It simplifies configuration. Example of a template in this case, iBGP between loopbacks, Next Hub self is set in this case, always send communities if that's not the default, hardwire BGP to version 4 if that's not the default, if that's not, if other versions are supported. In most cases, it's not. Use MD5 hash password with your eBGP as well as iBGP peer. Here is eBGP template example. Remove private ASs, remove bogons, basically. Use GTSM and use password. So this is just a template for eBGP. Use maximum prefix tracking. You can limit the AS path lengths inbound as well as outbound. You can limit the maximum AS path, sorry, the prefix lengths that you receive. So the key is configuration templates are very important. It helps you scale. Okay, wow. We're almost done on time. Hard to rush towards the end. Questions? Any questions? Thank you.